All right. Hear me okay? Cool. Um, Hello, everyone. Thanks for coming this morning. As Guy said, I'm Tom. I'm the head of engineering at Phenix. And what we do is we bring encryption capabilities to EVM developers. And we've seen like this importance of encryption in all chains. Guy mentioned it briefly, and it gets talked more and more about. And yeah, we'll see how we approach this problem and how we think we solve it in a very cool, interesting, and efficient way. Before that, let's take a step back for a second, and we'll kind of revisit the transparency problem of traditional blockchains. So MEV, right? Who knows MEV? By a show of hands, everyone, right? It's very obvious problem. We talked about it a lot. Basically, Alice sending a transaction and some evil operator basically puts his transactions before and extracts value. Obviously, when all the transactions, this evil person is basically taking advantage of all the mempool, all the transactions being transparent, being plain text. And obviously, when the transactions are encrypted, it's way harder to do. Um, Another example, and again, it's maybe not the best example, but it's very simple and easy for people to resonate with. Let's say we have a bid, like an auction on an NFT or whatever, and we have Alice here again. She bids 5 ETH on this NFT, and then this evil actor again harassing Alice, and at the very last second, he puts a bid of like not like an additional way on top of her bid because it's plain text. While she is probably offline or she's like not monitoring the things, and he basically wins the bid at the very last second, and we obviously don't want that. So encryption solves that as well. The point is that it becomes very obvious that encryption is coming to blockchains, and we'll see it more and more. And we're here to help mitigate these issues. Um, Very quick recap. We don't have a lot of time, so very quick recap on encryption. And this is I'm sure all of you guys are very smart and you know all of this already. Encryption 101. We have basically two keys. We have an encryption key in blue and we have a decryption key in red. And sometimes they're the same key, but sometimes there are different ones, but it doesn't matter for this context. And we basically have something that we want to encrypt or something sensitive that we want to keep private. So let's say this image. And when we do a mathematical operation, we basically somehow combine this image with the encryption key and we get an encrypted blob that no one else can read or understand what's going on under. Then we take this blob and do a decryption and we get back the original data or image in this case. This is traditional encryption, and it's cool and it works, and our entire lives are based on this. Now, FHE. The concept is pretty much the same, with a very important distinction. We still have an encryption key, and we encrypt our data, and we get an encrypted blob that basically means nothing. The beauty about NFT, about FHE, too many abbreviations, is that we can actually manipulate over the encrypted data without revealing it first, without decrypting it. So let's say I want to take this picture and I want to give it to ChatGPT and change something. So let's say we want to turn all the shirts red. What I have to do in this model is that I need to decrypt my data first, send it to ChatGPT, and let it do the work. I basically reveal my data. What FHE enables you to do is basically take your private data, this private blob here, and send it to ChatGPT encrypted. I also send the prompt encrypted. So I say, change all the shirts to red. That's encrypted as well. And then ChatGPT knows to do the manipulation and give me a different ciphertext. By looking at this, I don't know what this is. I don't see the underlying data, and I don't see the prompt. I don't know anything. I just know that this is different from this. And then when I eventually decrypt using the same key or another one, I receive the actual like changed data after that. FHE is actually, and all of this, all I've mentioned so far is actually a perfect fit for blockchains, because in blockchains we have multiple nodes, whether it execution nodes, verifiers, block builders, you name it, executing the same blocks to verify the results, to make sure to have consensus and all of that. FHE lets you do that without giving decryption capabilities to the people that running these transactions and these blocks. So we have different nodes. We have this transaction that is encrypted that we want to do like an encrypted manipulation over FHE. All of these nodes can do this manipulation without actually getting access to the underlying data. So they don't basically gain knowledge of anything. Now, one outstanding issue with this is who actually holds the decryption key. And that's an interesting question, because in the ChatGPT example, it was fairly easy. I had one user, let's say it's me, I control my keys. When I want to decrypt, I just decrypt. No one else gets access to my decryption key. But when we talk about blockchains, we have many users. We have many node operators. Who holds the key? If we give the key to every user, it's meaningless. If we give, because every user can then decrypt everything. If we give it to, let's say, miners, node operators, something like this, it's also meaningless, because then everyone, like, you have to give it to every node, and then every node can basically decrypt everything, and again, it's kind of pointless. For this, we use something called threshold decryption using MPC. MPC stands for multi-party computation. By show of hands, who is familiar with MPC? Amazing, almost everyone. I know you are. Cool. So, and threshold decryption is basically a method. When you see FHE protocols, when you see MPC protocols, like everyone actually uses a variation of threshold decryption. And what it lets you to do is basically take the decryption key and split it between multiple parties. And these multiple parties, you split it using a technique called secret sharing. And secret sharing, what that means is basically multiple parties can hold a share of this decryption key without having to then reconstruct it and use it to decrypt the ciphertext afterwards. So basically, it gives multiple people or multiple parties the ability to cooperate together in order to decrypt something without getting any knowledge about the original decryption key. Thus, it prevents them to actually do something malicious or like get hold of the key themselves. They have to use collaboration from everyone at the same time. This is basically a scheme of how it looks. So you have a ciphertext, you send it to a threshold decryptor mechanism. You have the SK1, SK2 is secret key, or the shares of the secret key. You split between the nodes, and the nodes can cooperate together to decrypt. So this is very cool, and it solves the problem of who holds the key. One issue is that, let's look at what we have for threshold FHE decryption currently. So after so-and-so years in research, we basically have two options to choose from. It's either very slow or not secure enough. And we obviously don't want to go, we were doing encryption, so we don't want to go with the not secure enough option. We have to kind of go to the too slow option. Now, I won't get too deep into it, but just remember the name, the slow option, and like, I'm calling it slow, but it's currently the state of the art, using a technique called noise flooding. And again, I'm not going to dive too deep into it. I'm not a cryptographer myself, so I don't want to embarrass myself here. But this technique is basically taking like 99% of the computation time. So decryption without noise flooding can be very, very, very quick. But this slows down the process by a lot. And when we see like, some benchmarks, we see more or less, between a few hundred milliseconds to maybe a second. It depends on the bit size, per decryption. And it sounds not a lot, right? It sounds fine. Throughput is about like 1 to 5 decryptions a second. Sounds manageable. But when we think of like actual real world use case, so let's say, we have like a DeFi app or something, people go in and they want to see their balances, right? And let's say they have 10 tokens of encrypted, like 10 encrypted tokens, and they want to see the balances of all of them. It's pretty fair request, right? If we have a thousand of these users, so we have 10,000 decryption requests. And if we have even five decryptions a second, which is like a best case scenario, it will take someone like around half an hour, maybe more, to actually decrypt everything. So half an hour to get a balance of my encrypted token, that doesn't sound right. So what we did to solve this, and this is by the way, like a very cool, our research team worked a lot on this, and this is groundbreaking. This is very cool. We basically, this noise flooding technique that we discussed before, we eliminated it. We managed to find a way, 5 minutes, really? We managed to find a way to eliminate the noise flooding. Of course, like, there are a couple of more details here. We ran into some, when you remove noise flooding, you need to kind of somehow go around it. So you have a bunch of different problems as well, but we're basically using some different techniques that I won't go into. And we managed to get very, very fast decryption protocol. And actually the paper got accepted to ACM CCS 25, and it's publishing next week. So stay tuned, very cool stuff. What we have currently, and this is big. Current state of the art is about like what we said before, like 5 decryptions a second, let's say. We managed to go to tens of thousands of decryptions per second, and this is not very optimized. We think it can even go up to like 100,000 decryptions a second, which is amazing, right? Which is basically solve the problem that we just discussed of encrypting the balances. Now, you can probably say, okay, this is very complicated, like, you probably need a different stack for this. You need a whole different blockchain. And we actually started by doing that. We had an L2, but we at some point realized that developers want to stay in their own stack. They want to use their familiar tools and everything. So we actually, this is why we built Coffee. Coffee is an FHE coprocessor that basically lets developers and users to use FHE in their own chains without like doing anything. Basically, it's effectively transparent, and we'll see it in a second. Basically, it's an off-chain component that reads events from the original chain, and it does the FHE computation in the background. The users don't even feel it. It just happens in the background. Your regular Ethereum Arbitrum transactions just happen as they are always. This is how it looks. Super simple to use. Solidity developers here? Anyone who wrote this is a very, very simplified version of a Solidity contract. You basically just import one line, our library, and then let's say you have a counter, you want to have it encrypted. You just change the type. You see EUINT there instead of a regular UINT. It stands for encrypted UINT. That's it. Then you basically can do, so this is FHE add. It's basically that you add 2 numbers. So you take the counter, increase it by 1. Very easy. We have some access control. This is important, but like at the end of the day, this is the gist. Like it's very simple. You just go to your regular smart contract, and that's it. Feel free to like scan it and see the docs. It's all really very, very simple. Do we have 2 minutes for a demo or no? Cool. So can we switch to the demo? What I want to show you right now, we've developed an app called Redact. It's a very simple demonstration of how it works. We're using coffee and using the threshold decryption that I just showcased. This paper, by the way, it's live. It's already on testnet. We already use this tech. Cool. So here you see Redact. What basically it lets you do is take your ERC20s and even your Ethereum tokens and encrypt them and send them to people and use them as encrypted with privacy. So this is an example of an encryption. You know, your usual stuff. You see the MetaMask, you confirm, you encrypt, that's it, bam, it's done. If you go to decrypt for a second, I don't know if you see this, but this is the balance. We made the UX simple to not, to make it as simple as possible for people, but this is encrypted. And this is very quickly gets decrypted using our novel threshold decryption mechanism. Yeah, if you do decrypt, so this is decrypt is basically to claim back your ETH that you just wrapped. So this is why you need to send a transaction, but obviously just to see your balance, you don't have to. You just send a request to the threshold network, and the result comes back. If you click, on the wallet, you see like all the balances. So this is Redact. Can we go back to the slides for a second? Thanks. Here's the link. I don't know if you can see it, test.redact.money. I encourage you all to go test, try it. It's very quick, it's very simple, and this is exactly what we aim for, and we're very, very happy with what we got. Yeah, so this is we saw. To summarize, we built Coffee to make encryption available to as many people and as many developers, as many users as possible. We had a major bottleneck with the decryption speed and performance, and we solved that. And now we feel like it's ready for production. This tech is very real. It's already implemented, not fully optimized. We're still getting better and better results. But Coffee is live. The decryption network and threshold protocol that I showcased is live. And we saw Redact to see it in action. So yeah, we're very excited about it. Thank you very much for listening.